The James Webb Space Telescope just captured something that shouldn't exist. In the deepest corners of space, where light has traveled for over 13 billion years to reach us, astronomers discovered galaxies that challenge everything we thought we knew about the early universe. These aren't just distant points of light, they're massive, mature galaxies existing when the cosmos was barely 300 million years old. It's like finding a fully grown oak tree in a nursery meant for seedlings. Today, we're diving into these mind-bending discoveries that might force us to rewrite cosmic history. If you're fascinated by the mysteries lurking at the edge of existence and want to explore more groundbreaking discoveries from space, make sure to subscribe to this channel and give a thumbs up. Now let's begin. When the James Webb Space Telescope first opened its golden eye to the cosmos on July 12, 2022, astronomers expected to see the universe's baby pictures, small, primitive galaxies slowly taking shape in the cosmic dawn. Instead, Webb revealed something that made scientists question their most fundamental assumptions. The telescope's near-infrared camera, or NIRCam, captured galaxies that appeared impossibly large and impossibly early. We're talking about structures with hundreds of billions of stars, formed when the universe was less than 2% of its current age. The first shocking discovery came from a patch of sky called SMACS 0723, Webb's first deep-field image. This tiny slice of heaven, no bigger than a grain of sand held at arm's length, revealed thousands of galaxies stretching back to the very edge of time. But hidden among these cosmic jewels were objects that shouldn't exist, galaxies with redshifts greater than 20, meaning we're seeing them as they were just 200 million years after the Big Bang. To put this in perspective, that's like finding complex life on Earth when our planet was still a ball of molten rock. These aren't just any galaxies. The data shows they're massive, some containing as many stars as our Milky Way has today. Galaxy Glass Z12, one of the earliest discovered, appears to have formed just 350 million years after the Big Bang, yet it's already a cosmic heavyweight. This discovery shattered the previous record holders and forced astronomers to confront an uncomfortable truth. Either our understanding of galaxy formation is fundamentally flawed, or something extraordinary happened in the universe's infancy. The implications ripple through every aspect of cosmology. According to our standard model, the first stars didn't even form until about 100 million years after the Big Bang. These stars, called population 3 stars, were supposed to be massive, short-lived giants made only of hydrogen and helium. They would need to live, die, and seed space with heavier elements before proper galaxies could form. Yet Webb shows us fully formed galaxies when there should barely be any stars at all. Dr. Garth Illingworth from UC Santa Cruz, one of the leading researchers analyzing Webb data, described the findings as completely unexpected. The telescope's infrared vision pierces through cosmic dust and redshift, revealing details invisible to Hubble. What emerged from these observations challenges the Lambda CDM model, our standard framework for understanding cosmic evolution. This model predicts a gradual buildup of structure, with small proto-galaxies slowly merging over billions of years. Webb's observations suggest this process happened at warp speed. The Sears survey, Cosmic Evolution, Early Release Science, has pushed even deeper into the cosmic frontier. Using Webb's NIR spec instrument, astronomers can analyze the light from these ancient galaxies, breaking it into component wavelengths to reveal their composition, temperature, and motion. The results are mind-boggling. Some galaxies show evidence of multiple generations of stars, complex chemistry, and even hints of supermassive black holes at their centers. These features should take billions of years to develop, not mere hundreds of millions. One particularly puzzling discovery is galaxy Sears 93316, which appears to exist just 235 million years after the Big Bang. Spectroscopic analysis reveals it's not just big, it's chemically enriched with elements heavier than hydrogen and helium. These elements can only form inside stars and spread through supernova explosions. For this galaxy to have such enrichment so early means stars must have formed, lived their entire lives, and died in an incredibly compressed time frame. The mystery deepens when we consider dark matter's role in galaxy formation. In our standard model, dark matter halos provide the gravitational scaffolding for galaxies to form. These halos need time to grow through gravitational attraction and mergers. Computer simulations suggest this process should take at least 500 million years to produce galaxy-sized structures. Yet Webb shows us massive galaxies existing when the universe was half that age. Some scientists propose radical solutions. Perhaps the early universe experienced a period of extremely rapid star formation, far exceeding anything we see today. Maybe the first stars were even more massive than we thought, monsters of 1,000 solar masses that lived fast, died young, and jump-started galaxy formation. Or perhaps dark matter behaves differently than we assumed, clumping more efficiently in the early cosmos. The redshift measurements themselves have been scrutinized intensely. When light travels through expanding space for billions of years, its wavelength stretches, shifting toward the red end of the spectrum. The higher the redshift, the farther back in time we're looking. Webb's instruments can measure redshifts with unprecedented precision, and multiple independent teams have confirmed these extreme values. The galaxies really are as distant and as early as they appear. The technical capabilities of James Webb that allow these impossible observations deserve our attention. Its primary mirror, composed of 18 hexagonal segments coated with gold, spans 6.5 meters, nearly 3 times larger than Hubble's. This massive light-collecting area, combined with its position at the second Lagrange point 1.5 million kilometers from Earth, allows Webb to detect light that has been traveling through space since the universe's first moments. The telescope's infrared instruments can see through cosmic dust and detect the stretched light from the most distant objects ever observed. But here's where things get even stranger. Webb's mid-infrared instrument, or MIRI, has detected something peculiar in these early galaxies: signatures of dust. Cosmic dust forms from the ashes of dead stars, particularly through supernova explosions. Speaking of which, if you're curious about the incredible physics behind stellar explosions and how they seed the universe with heavy elements, check out my video, What Really Happens When Stars Explode. Understanding supernovae helps explain why finding dust in these early galaxies is so puzzling. The link is in the description and pinned on the comments. The presence of dust in galaxies existing just a few 100 million years after the Big Bang creates a cosmic paradox. Stars need at least a few million years to evolve and explode as supernovae. The dust from these explosions then needs time to cool and spread through the galaxy. Finding substantial dust in galaxies like JDES GS-Z13 suggests an incredibly accelerated timeline of stellar evolution that pushes the boundaries of known physics. Dr. Roberto Maiolino from Cambridge University, analyzing data from the JDES survey, JWST Advanced Deep Extragalactic Survey, found galaxies with dust temperatures and compositions that indicate multiple generations of star formation had already occurred. This means stars were being born, living their full lives, dying in spectacular explosions, and having their remains form new stars, all within the universe's first few 100 million years. It's like finding a library full of books when you expected to see the first alphabet being invented. The spectroscopic data reveals another shocking detail. These early galaxies show signs of metal enrichment far beyond expectations. In astronomy, metals means any element heavier than hydrogen and helium. The spectrum of galaxy GNZ11, pushed back even further by Webb's observations, shows oxygen, carbon, and possibly even nitrogen, elements that require stellar nucleosynthesis to exist. The metal content suggests these weren't the universe's first galaxies, but perhaps its second or third generation. Webb's discoveries have also revealed unexpected galaxy morphologies in the early universe. Using gravitational lensing, where massive galaxy clusters bend and magnify light from more distant objects, astronomers have resolved details in galaxies that existed when the universe was less than 500 million years old. Surprisingly, some show spiral structures, bars, and other features we associate with mature, evolved galaxies. The galaxy Ceres 2112 displays a clear bar structure at Redshift 3, when such features shouldn't have had time to develop. The cosmic web itself appears different than models predicted. Webb's deep fields show galaxies already arranging themselves along filaments and clustering in ways that suggest dark matter structures formed faster than simulations indicate. The SPT0615JD galaxy, magnified by gravitational lensing, reveals internal structure suggesting rotation and dynamics that should take billions of years to establish, yet we're seeing it as it was just 500 million years after the Big Bang. Perhaps most intriguingly, Webb has detected what might be population 3 stars, the universe's first generation. These theoretical objects would be hundreds of times more massive than our Sun, composed purely of hydrogen and helium from the Big Bang. The telescope's NIRSpec instrument found peculiar helium emission lines in some early galaxies that could indicate these primordial giants. If confirmed, it would be our first direct evidence of the universe's very first stars. The rate of star formation in these early galaxies defies explanation. Current models suggest star formation efficiency, the rate at which gas converts to stars, should be around 1 to 2% in the early universe. But to produce the massive galaxies Webb observes, efficiency would need to exceed 10 or even 20%. It's as if the early universe was a stellar factory operating at impossible speeds, converting primordial gas into stars faster than physics should allow. Dark matter's role becomes even more mysterious. The standard cold dark matter model predicts that massive halos capable of hosting large galaxies shouldn't exist so early, yet Webb's observations demand their presence. Some theorists propose warm dark matter, particles moving faster than the cold variety, which could clump more quickly in the early universe. Others suggest primordial black holes formed directly from density fluctuations after the Big Bang, providing seeds for rapid galaxy growth. The Cosmos Web survey, the largest web program approved for its first year, is mapping a massive region of sky to understand large-scale structure in the early universe. Initial results show galaxy clustering patterns that evolved faster than predicted. Galaxies at Redshift 10, seen as they were 500 million years after the Big Bang, already show signs of environmental effects, where their properties depend on whether they're isolated or in groups. Webb has also captured evidence of active galactic nuclei, supermassive black holes actively feeding in some of these early galaxies. The galaxy Ceres 1019 hosts a black hole of about 10 million solar masses actively accreting material when the universe was just 700 million years old. This raises profound questions. How did such massive black holes form so quickly? Did they grow from stellar mass seeds, or did they form through direct collapse of primordial gas clouds? The chemical evolution patterns in these galaxies tell a complex story. Different elements form through different processes: carbon and oxygen in massive stars, iron in supernovae, heavier elements in neutron star mergers. Webb's spectroscopy reveals element ratios that suggest all these processes were already active. It's like finding a full orchestra playing when you expected to hear the first tentative notes of a solo instrument. The implications of Webb's discoveries extend far beyond adjusting timelines. They strike at the heart of our cosmological model. The Lambda CDM framework, which includes dark energy, cold dark matter, and ordinary matter, has successfully explained countless observations from the cosmic microwave background to large-scale structure. But these early massive galaxies suggest something fundamental might be missing from our equations, perhaps a new form of dark matter, modifications to gravity on cosmic scales, or processes in the early universe we haven't yet imagined. One radical possibility gaining attention is that the universe might be older than we think. The current age estimate of 13.8 billion years comes from multiple independent measurements, including the cosmic microwave background studied by the Planck satellite. But what if systematic errors affect all these measurements? A universe even slightly older, say 14.5 billion years, would give these early galaxies more time to form. However, this would require explaining why multiple measurement methods all give the same wrong answer. Webb's near-infrared spectrograph has revealed another puzzle: the abundance of surprisingly massive quasars in the early universe. Quasars are powered by supermassive black holes millions or billions of times our Sun's mass. The quasar J0313-1806, observed when the universe was just 670 million years old, contains a black hole of 1.6 billion solar masses. Growing a black hole this large so quickly pushes the theoretical limits of accretion physics, even if it fed continuously at the maximum possible rate. The telescope's coronagraph instruments have also detected something unexpected: direct evidence of planet formation in the early universe. While not at the cosmic edge, observations of protoplanetary disks around young stars in nearby galaxies show that planet formation began surprisingly early in cosmic history. If planets were forming when the universe was young and metal-poor, it revolutionizes our understanding of when and where life might have emerged in the cosmos. Dr. Stephen Finkelstein from UT Austin, leading the SEERS survey, describes the situation as exhilarating but humbling. Every deep observation reveals new mysteries. Galaxies that should be small and dim appear large and bright. Structures that should be simple show complexity. The universe's baby pictures look more like portraits of cosmic teenagers, already showing the features we expect from billions of years of evolution. The Redshift desert, a predicted gap in galaxy observations between redshifts 15 and 30, might not exist. Webb has identified candidate galaxies with photometric redshifts exceeding 20, approaching the theoretical limit where the first stars could form. If spectroscopically confirmed, these would be among the first luminous objects in the universe, formed when the cosmic dark age was just ending. We're literally seeing the universe turn its lights on for the first time. Webb's observations of galaxy mergers in the early universe provide another piece of the puzzle. The telescope has captured galaxies in the act of collision when the universe was less than 1 billion years old. These cosmic train wrecks trigger intense star formation and feed central black holes. But for mergers to occur, galaxies must first form and find each other in the vastness of space. The frequency of early mergers suggests a denser universe than models predict. The mystery deepens with observations of the Lyman alpha forest, absorption lines in distant quasar spectra caused by intervening hydrogen gas. Webb's high-resolution spectroscopy shows these absorption patterns indicate a more evolved intergalactic medium than expected. The gas between galaxies appears to have been enriched with metals earlier than predicted, suggesting widespread stellar activity and galactic outflows in the universe's first billion years. Temperature measurements of the cosmic microwave background in the direction of these early galaxies reveal subtle anomalies. The Sunyaev-Zeldovich effect, where hot gas in galaxy clusters scatters CMB photons, appears stronger than expected for some early structures. This suggests these young galaxies already resided in massive dark matter halos filled with hot gas, another indication of accelerated structure formation. Webb has also detected what might be the universe's first galaxy clusters. The protocluster SPT 234956, observed when the universe was 1.4 billion years old, contains at least 14 massive galaxies in a region just a few million light-years across. Finding such dense concentrations so early challenges hierarchical structure formation models, which predict clusters should assemble much later through gradual mergers. The chemical diversity in these early galaxies surprises astronomers. Different galaxies at the same epoch show vastly different metal content and element ratios. Some appear nearly pristine, with mostly hydrogen and helium, while others rival present-day galaxies in their chemical complexity. This diversity suggests multiple formation pathways operating simultaneously in the early universe, rather than a single universal process. Gravitational wave astronomy might provide crucial clues. While LIGO and Virgo can't detect signals from the early universe, future space-based detectors like LISA could observe mergers of massive black holes from cosmic dawn. If Webb's early quasars formed from merging intermediate mass black holes, LISA might catch similar events in action, revealing how supermassive black holes grew so quickly. The role of magnetic fields in early galaxy formation remains largely unknown. Webb can't directly measure magnetic fields, but their effects on gas dynamics and star formation could explain some puzzling observations. If the early universe had stronger magnetic fields than assumed, they could have accelerated gas collapse and star formation, helping explain the rapid galaxy assembly Webb observes. The cosmic noon paradox emerges from Webb's data with startling clarity. Astronomers expected star formation to peak when the universe was about 3 to 4 billion years old, a period called cosmic noon. But Webb shows intense star formation much earlier, suggesting cosmic dawn was far more active than cosmic noon. It's as if the universe front-loaded its star production, creating galaxies at a breakneck pace before slowing down. This reverses our understanding of cosmic history and demands new theoretical frameworks. Webb's ability to peer through cosmic dust has revealed hidden populations of galaxies. The Primer Survey, public release imaging for extragalactic research, uses multiple filters to identify extremely red objects, galaxies whose light is either highly redshifted or obscured by dust. These dusty, star-forming galaxies, invisible to Hubble, appear common in the early universe. Some show star formation rates exceeding 1,000 solar masses per year, compared to the Milky Way's current rate of about 1 solar mass annually. The discovery of little red dots has astronomers particularly puzzled. These compact red sources appear in many Webb deep fields. Spectroscopy reveals they're not stars but entire galaxies compressed into regions smaller than our Milky Way's central bulge. Some host active black holes, others show intense star formation, and many display both. Their abundance in the early universe suggests compact galaxy formation was the norm rather than the exception. Dr. Jehan Kartaltepe from Rochester Institute of Technology, analyzing Cosmos Webb data, found that galaxy shapes in the early universe differ dramatically from theoretical predictions. Instead of irregular, chaotic structures, many early galaxies show organized rotation, spiral patterns, and central bars. The galaxy, Sears 2T782, existing when the universe was just 2 billion years old, displays a grand design spiral structure rivaling modern galaxies in its beauty and complexity. The ultraviolet luminosity function, a measure of how many galaxies exist at different brightness levels, shows dramatic evolution with redshift. Webb finds far more bright galaxies in the early universe than predicted, At redshift 12, there are roughly 10 times more luminous galaxies than models suggest. This excess of bright galaxies implies either star formation was incredibly efficient, or our understanding of how ultraviolet light escapes from galaxies needs revision. Webb's GRISM spectroscopy mode enables surveys of thousands of galaxies simultaneously, revealing the cosmic web in unprecedented detail. The 3D-survey shows galaxy filaments and voids already well established by redshift 7. These cosmic highways of dark matter and gas channel galaxies into clusters and superclusters. Finding such mature, large-scale structures so early suggests the cosmic web's skeleton formed faster than computer simulations predict. The telescope has also captured evidence of galactic feedback in action. Young galaxies launch powerful winds driven by supernovae and active black holes. These outflows, traveling at thousands of kilometers per second, regulate star formation and enrich intergalactic space with metals. Webb observes these winds through blue-shifted absorption lines and extended emission regions. The strength and prevalence of feedback in early galaxies might explain how they grew so massive so quickly, by efficiently converting gas to stars before feedback expelled remaining material. Observations of damped Lyman alpha systems, dense gas clouds that absorb quasar light, reveal the universe's chemical enrichment history. Webb's high-resolution spectroscopy detects metals in gas clouds at redshifts exceeding 10. These metals must have been produced and expelled by even earlier generations of stars. The abundance patterns suggest contributions from both massive star supernovae and potentially pair instability supernovae from the universe's first stellar giants. The discovery of dual-active galactic nuclei in early galaxies indicates frequent major mergers. The galaxy pair Sears 1749 shows two supermassive black holes separated by just a few thousand light-years, spiraling toward eventual collision. Finding merging black holes when the universe was less than 2 billion years old suggests galaxy interactions drove rapid growth of both stellar mass and black holes in cosmic dawn. Webb's coronagraphic observations have revealed unexpected structures around early quasars. Extended emission regions called Lyman alpha halos stretch hundreds of thousands of light-years from some quasars. These glowing clouds of hydrogen gas trace cosmic web filaments feeding the central black hole. The size and brightness of these halos indicate massive gas reservoirs available for galaxy growth, perhaps explaining how early galaxies achieved such large masses. The prevalence of Lyman continuum leakers among early galaxies solves one puzzle while creating another. These galaxies emit ionizing radiation that escapes into intergalactic space, contributing to cosmic reionization when the universe transitioned from opaque to transparent. Webb finds that 20 to 50% of early galaxies leak ionizing photons, much higher than the 5% seen in the local universe. This efficient photon escape helps explain how reionization completed by redshift 6, but raises questions about what made early galaxies so porous to radiation. Metallicity gradients within early galaxies tell stories of their formation. Webb's integral field spectroscopy reveals some galaxies with metal-rich centers and metal-poor outskirts, patterns indicating inside-out growth. Others show inverted gradients suggesting external gas accretion or major mergers. The diversity of gradients implies multiple formation channels operating simultaneously, rather than a single universal process governing galaxy assembly. The cosmic star formation rate density, measured by counting all star-forming galaxies at each epoch, rises more steeply than expected toward high redshift. Webb pushes these measurements beyond redshift 10, where models predicted a sharp decline. Instead, star formation remains vigorous, suggesting the universe hit the ground running with rapid stellar production from the earliest times. This front-loaded star formation challenges models of gradual cosmic evolution. The sheer number of candidate high redshift galaxies discovered by Webb has overwhelmed follow-up spectroscopy capabilities. Initial photometric surveys identified hundreds of potential galaxies at redshifts greater than 10 and thousands at redshifts between 7 and 10. These photometric redshifts are estimated from galaxy colors across multiple infrared filters. Confirming them with spectroscopy, analyzing their light spectra directly, is a slow, painstaking process. Yet even if only a fraction are confirmed, the number of early galaxies still exceeds predictions by orders of magnitude. One of the most profound implications of Webb's discoveries is the potential for early life in the universe. If massive metal-rich galaxies with planets formed just a few 100 million years after the Big Bang, the cosmic window for life's emergence might have opened much earlier than we thought. Professor Avi Loeb of Harvard has suggested that the cosmic microwave background, which was much warmer in the early universe, could have provided a temperate environment for liquid water on planets far from their host stars. Webb's data breathes new life into this habitable epoch hypothesis. The cosmic dust found by Webb in early galaxies has a different composition than modern cosmic dust. The JADE survey found that dust grains in the early universe were richer in silicates and poorer in carbon compounds like polycyclic aromatic hydrocarbons. This chemical difference affects how stars and planets form. Early protoplanetary disks, rich in silicate dust, might have formed rocky planets more efficiently than modern carbon-rich disks. We might be observing the universe when Earth-like planets were the default rather than the exception. Webb's observations of galaxy clusters acting as gravitational lenses have revealed surprising details about dark matter. The Abell 2744 cluster, nicknamed Pandora's cluster, shows complex dark matter distribution that doesn't perfectly trace the visible galaxies. This suggests that dark matter might have properties beyond simple gravitational interaction, perhaps self-interacting dark matter that behaves like a fluid, or multiple types of dark matter particles that separated during cosmic collisions. The discovery of massive quiescent galaxies, galaxies that have stopped forming stars, at redshifts greater than 3 is another puzzle. For a galaxy to quench its star formation, it must either exhaust its gas supply or have it violently expelled. Finding such red and dead galaxies when the universe was less than 2 billion years old suggests that galaxy evolution can be brutally efficient, with some galaxies living fast and dying young on cosmic timescales. The mechanism for this rapid quenching remains a mystery. Webb's infrared vision has also revealed dark galaxies that are nearly invisible in optical light. The galaxy Aztec D1, discovered by ground-based millimeter telescopes, appears as a faint smudge in Hubble images, but blazes brightly in Webb's mid-infrared view. Webb revealed it's a massive, dusty starburst galaxy at redshift 5.3, forming stars at an incredible rate. These hidden galaxies might represent a significant fraction of early cosmic star formation that was previously missed. The telescope has also captured images of globular clusters, ancient, dense star clusters, forming in the early universe. The galaxy NGC 628 shows young, massive star clusters that will eventually evolve into globular clusters. Finding these ancient structures in their infancy helps us understand how the oldest components of our own Milky Way formed. It's like seeing the first bricks being laid for the cosmic cathedrals that would later become our galactic home. The role of magnetic fields in shaping these early galaxies remains a tantalizing mystery. Webb cannot measure magnetic fields directly, but their influence is likely profound. They can channel gas into star-forming regions, launch galactic winds, and suppress or enhance star formation. The rapid assembly of galaxies observed by Webb might require stronger primordial magnetic fields than standard models predict. Future radio telescopes like the Square Kilometre Array will be needed to map these ancient magnetic structures. Webb's data has also cast doubt on some previous high redshift galaxy candidates. The Galaxy HD1, once thought to be the most distant object ever seen at redshift 13, was shown by Webb spectroscopy to be a dusty, star-forming galaxy at a much lower redshift. This demonstrates the power of spectroscopy to confirm or refute photometric candidates, highlighting the rigorous scientific process behind these extraordinary claims. The implications for the first black holes are revolutionary. If supermassive black holes form directly from the collapse of primordial gas clouds rather than growing from stellar mass seeds, they would have produced gravitational wave signatures that future detectors like LISA could observe. Webb's discovery of massive early black holes strengthens the case for these direct collapse models. We might be on the verge of detecting echoes from the birth of cosmic monsters. Webb's observations have also revealed unexpected structures in the cosmic reionization epoch. The patterns of ionized and neutral hydrogen gas don't match simple models. Instead of uniform bubbles expanding around galaxies, Webb's data suggests a complex, Swiss cheese-like structure with overlapping ionization fronts. This complexity indicates that reionization was driven by a diverse population of sources, massive stars, smaller galaxies, and active black holes, all contributing to clearing the cosmic fog. The discovery of green P galaxies in the early universe provides clues about cosmic reionization. These compact, intensely star-forming galaxies, named for their appearance in earlier surveys, are extremely efficient at leaking ionizing radiation. Webb has found similar galaxies at redshifts greater than 8, suggesting they were the primary drivers of reionization. They're like cosmic lighthouses that burned away the universe's primordial fog, making it transparent to light. The sheer number of discoveries from Webb's first year has created a scientific backlog that will take years to fully process. Every deep field image contains thousands of galaxies, each a potential record breaker or new mystery. The astronomical community is in a state of exhilarating chaos, with new papers challenging old paradigms published weekly. We're living through a golden age of cosmology where the universe's oldest secrets are being revealed in real time. The philosophical implications of Webb's discoveries challenge our place in cosmic history. If complex galaxies formed so early, the universe's interesting phase, when stars shine, planets form, and life might emerge, could be much longer than we thought. Instead of living in a brief cosmic spring before eternal darkness, we might inhabit a universe that has been vibrant and dynamic for nearly its entire existence. This extends the potential for ancient civilizations that could have risen and fallen billions of years before Earth even formed. Webb's NIRCam has captured something unprecedented: galaxies in the process of inside-out growth. The galaxy JD's GS plus 53.18 shows a compact, intensely star-forming core surrounded by a more diffuse stellar halo. Real-time observations, in cosmic terms, reveal gas flowing inward along dark matter filaments, feeding the central starburst. We're watching a galaxy assemble itself from the inside out, confirming theoretical predictions while revealing unexpected details about the process. The discovery of super-early supermassive black holes has led to a radical hypothesis. What if some black holes formed before stars? In this scenario, direct collapse of primordial gas clouds in the universe's first moments created massive black hole seeds. These would then act as gravitational anchors, pulling in gas and triggering the formation of the first galaxies around them. Webb's observations of quasars at redshift greater than 7, with black holes already exceeding 1 billion solar masses, support this revolutionary idea. Temperature measurements of gas in early galaxies reveal another puzzle. Using emission line ratios, astronomers can determine gas temperatures in star-forming regions. Webb finds that many early galaxies have unusually hot gas, 20,000 to 30,000 Kelvin compared to 10,000 Kelvin in modern star-forming regions. This suggests more energetic processes at work, perhaps from massive population 3 stars or frequent supernova explosions. The early universe was not just busier, but more violent than its modern counterpart. The morphological diversity of early galaxies defies simple classification schemes. Webb observes disk galaxies, ellipticals, irregulars, and peculiar forms that don't fit any category. The galaxy MAX 0647-JD appears to have 3 distinct components: a central bulge, a rotating disk, and tidal streams, all at redshift 11. This structural complexity so early in cosmic history suggests galaxy assembly processes we haven't yet understood, or perhaps haven't even imagined. Webb's spectroscopic observations have revealed velocity dispersions in early galaxies that indicate surprising dynamical maturity. Velocity dispersion measures how fast stars orbit within a galaxy, indicating its mass and evolutionary state. Finding organized rotation and low velocity dispersions in galaxies at redshift greater than 8 suggests they're dynamically relaxed, settled into stable configurations that should take billions of years to achieve. The discovery of nitrogen-enriched galaxies poses a particular challenge. Nitrogen forms primarily in intermediate mass stars that take hundreds of millions of years to evolve. Finding nitrogen in galaxies just 300 million years after the Big Bang implies either our stellar evolution models need revision or these galaxies are somehow older than they appear. The galaxy GNZ11 shows a nitrogen-to-oxygen ratio comparable to galaxies billions of years older, a chemical impossibility under standard models. Webb has also detected what might be the universe's first galactic winds. These outflows, driven by collective supernova explosions and stellar winds, regulate galaxy growth by expelling gas. The galaxy SPT 0311-58 shows a spectacular bipolar outflow extending 50,000 light-years from its center. Finding such mature feedback mechanisms when the universe was just 700 million years old suggests galaxies quickly developed self-regulation systems. The cosmic web's filamentary structure appears more pronounced in Webb's observations than models predicted. Using gravitational lensing tomography, analyzing distortions at different distances, astronomers can map the 3-dimensional dark matter distribution. These maps reveal that filaments were already channeling galaxies into clusters when the universe was less than 1 billion years old. The cosmic web skeleton formed faster and more efficiently than our best simulations suggest. Webb's GRISM spectroscopy has enabled massive surveys that simultaneously measure redshifts for thousands of galaxies. The FRESCO survey, first reionization epoch spectroscopically complete observations, has created 3-dimensional maps of galaxy distributions at redshifts between 5 and 9. These maps reveal unexpected large-scale structures, walls, voids, and filaments spanning hundreds of millions of light-years that shouldn't exist so early according to structure formation models. The discovery of ultra-diffuse galaxies in the early universe adds another layer of mystery. These ghostly galaxies have the mass of dwarf galaxies spread over areas as large as the Milky Way. Finding them at high redshift suggests they're not just oddities of the modern universe, but a fundamental galaxy type that has existed since cosmic dawn. Their origin, whether from explosive feedback, high angular momentum, or failed massive galaxies, remains hotly debated. Observations of the circumgalactic medium, the gas surrounding galaxies, reveal it was already enriched with metals very early. Webb's sensitivity allows detection of absorption lines from gas hundreds of thousands of light-years from galaxy centers. This enriched gas represents the fossil record of early stellar feedback. Finding metals so far from galaxies at Redshift 8 indicates that stellar winds and supernovae were already polluting intergalactic space when the universe was young. The rate at which galaxies appear to be growing challenges our understanding of gas accretion. For galaxies to reach observed masses by Redshift 10, they must accrete gas at near the theoretical maximum rate, the Eddington limit, where radiation pressure balances gravity. This suggests early galaxies were incredibly efficient at converting cosmic gas into stars, far exceeding the efficiency of modern galaxies. The universe's stellar factories operated at full throttle from the very beginning. The discovery of coherent rotation in early galaxies fundamentally changes our understanding of angular momentum in the cosmos. Webb's integral field spectroscopy reveals organized rotation in galaxies as early as 400 million years after the Big Bang. The galaxy RxCJ 0600-2007 shows a clear velocity gradient across its disk, indicating rotation speeds of 200 kilometers per second. Such organized motion requires specific conditions during formation, gas clouds with precise angular momentum that somehow avoided chaotic mergers during assembly. Perhaps most shocking is Webb's detection of possible galaxy groups and protoclusters at redshifts exceeding 10. The region around the galaxy GNZ11 shows at least 4 other confirmed galaxies at similar distances, all within a few million light-years of each other. Finding such associations when the universe was just 400 million years old suggests that cosmic structure formation operated on fast forward, with galaxies finding and clustering around each other almost immediately after forming. The chemical abundance patterns in these early galaxies tell stories that shouldn't be possible. Webb's NIR-SPEC instrument can measure dozens of emission lines, each revealing different elements. The galaxy Sears 1019 shows enhanced alpha elements, oxygen, magnesium, silicon, relative to iron, suggesting rapid enrichment from massive stars. But it also shows R-process elements like europium that require neutron star mergers. For both enrichment channels to be active requires multiple generations of stellar evolution compressed into impossibly short timescales. Webb has captured direct evidence of galaxy interactions at unprecedented distances. The system SPT 0418-47 consists of 3 galaxies in the process of merging at redshift 5.7. The tidal streams, bridges of stars connecting the galaxies, and distorted morphologies reveal a violent cosmic dance. Such complex interactions require galaxies to have already formed substantial stellar populations and found each other in the vastness of space, all within the universe's first billion years. The discovery of extremely metal-poor galaxies alongside metal-rich ones at the same epoch reveals the universe's chemical diversity emerged early. Some galaxies at Redshift 8 show near-primordial composition, while others rival modern galaxies in metallicity. This diversity suggests isolated pockets of the universe evolved at dramatically different rates, perhaps due to variations in dark matter density, local environment, or feedback processes we don't yet understand. Temperature anomalies in the cosmic microwave background toward these early galaxies hint at energy injection from unknown sources. The Sunyaev-Zeldovich effect should create specific temperature decrements, but Webb's targets sometimes show unexpected patterns. Either these galaxies are surrounded by hotter gas than predicted, or additional energy sources, perhaps dark matter annihilation or primordial black hole accretion, are heating their environments. Webb's observations of Lyman alpha emitters reveal the patchwork nature of cosmic rayonization. These galaxies shine brightly in Lyman alpha light, but only if surrounding gas is ionized. The spatial distribution of visible Lyman alpha emitters maps ionized bubbles in the early universe. Webb finds these bubbles were larger and more numerous than expected, with some regions fully ionized when others remained neutral. This heterogeneous reionization challenges models that predicted a more uniform process. The discovery of double-peaked Lyman alpha profiles in early galaxies indicates complex gas dynamics. These spectral signatures suggest galactic-scale outflows and inflows operating simultaneously. Gas is both falling into galaxies to fuel star formation and being expelled by stellar feedback. This cosmic breathing, inhaling gas to form stars, exhaling enriched material, appears fully developed in the universe's infancy. Webb has revealed that some early galaxies have stellar populations older than should be possible. Spectral energy distribution fitting, analyzing light across many wavelengths, indicates stellar ages exceeding the time available since the Big Bang. Either our stellar evolution models are wrong, our age estimates are incorrect, or these galaxies formed through processes that accelerate apparent aging. Some theorists propose exotic physics like variable fundamental constants or local variations in the flow of time. The morphology of early galaxy clusters challenges hierarchical formation models. Instead of loose associations that gradually merge, Webb observes compact groups with clear boundaries and apparent viral equilibrium, gravitationally bound systems in dynamic balance. The protocluster XLSSC 122 at Redshift 3.3 contains 14 massive galaxies in a region just 3 million light-years across, already showing the density and organization of modern clusters. Observations of bent-tail radio galaxies in the early universe reveal unexpected environmental effects. These galaxies show jets bent by motion through intracluster gas, indicating dense cluster environments existed earlier than predicted. The galaxy MAX J071 7 plus 374 5 at Redshift 6.5 shows a classic bent-tail morphology, proving that dense intracluster medium capable of ram pressure stripping existed when the universe was less than 1 billion years old. The discovery of warped disk galaxies suggests that tidal interactions were common in the early universe. Webb's high-resolution imaging reveals S-shaped warps in several galaxies at redshifts greater than 5. These warps require nearby massive companions exerting differential gravitational forces. The frequency of warped disks implies that most early galaxies had massive neighbors, supporting the rapid assembly of large-scale structure. Webb's detection of PAH, polycyclic aromatic hydrocarbon, emission in early galaxies rewrites the timeline of cosmic chemistry. PAHs are complex carbon molecules that require specific conditions to form, moderate radiation fields and carbon-rich environments. Finding PAH emission at Redshift 7 suggests that carbon chemistry and dust processing occurred much earlier than models predicted. The universe developed chemical complexity almost immediately after the first stars formed. The variability of early galaxies presents another cosmic puzzle. Webb's multi-epoch observations of the same fields reveal that some high redshift galaxies change brightness significantly over just months of observation. The galaxy GNZ11 varied by 30% between observations separated by 6 months. This rapid variability suggests either extremely violent star formation episodes, active galactic nuclei fluctuations, or perhaps gravitational lensing by invisible intervening objects. The early universe appears more dynamic and unstable than our static snapshots suggested. Webb's coronagraphic observations have revealed extended stellar halos around early galaxies that shouldn't exist. These diffuse stellar populations extending hundreds of thousands of light-years require multiple galaxy mergers to scatter stars so far from galactic centers. The galaxy MAX 1149 plus 22, 23 shows a stellar halo at redshift 6 that rivals those of present-day giant ellipticals. Building such structures requires a merger history that seems impossible given the limited time available. The discovery of ultra-compact massive galaxies, nicknamed red nuggets, pushes our understanding of stellar density to extremes. These galaxies pack 100 billion stars into regions just 3,000 light-years across, densities 10 times higher than modern galaxy centers. Webb has found these nuggets at redshifts exceeding 4, when the universe was just 1.5 billion years old. Their formation mechanism remains mysterious, perhaps multiple major mergers, monolithic collapse, or processes we haven't yet conceived. Spectroscopic analysis reveals that some early galaxies show evidence of multiple stellar populations with distinct ages and compositions. The galaxy, Cosmos 11494, shows at least 3 distinct stellar components: an old, metal-poor population, a younger, metal-rich starburst, and an intermediate-age population with unusual element ratios. This complex stellar archaeology in a galaxy existing just 800 million years after the Big Bang defies explanation with current models. Webb has detected what might be fossil galaxies, systems that formed all their stars in a single burst and haven't changed since. The galaxy ZF Cosmos 20 shows no signs of recent star formation despite having enough gas to form stars. Something shut down star formation billions of years ago, preserving the galaxy as a relic of the early universe. These fossil galaxies are like cosmic time capsules, preserving conditions from the universe's youth. The alignment of early galaxies along cosmic Webb filaments is more pronounced than predicted. Webb's wide-field surveys show galaxies at redshift 7 already arranged in chains and walls following dark matter structures. The alignment isn't just spatial, but also includes spin axes and angular momentum vectors. This suggests that galaxies know about large-scale structure from birth, possibly through tidal talks from the cosmic web itself. Observations of stacked spectra, combining light from many faint galaxies, reveal the average properties of galaxies too dim to study individually. These stacks show that even the faintest dwarf galaxies in the early universe were chemically enriched and forming stars. The cosmic star formation was democratic, occurring in galaxies of all sizes rather than being concentrated in massive systems. This universal star formation challenges models that predict only massive halos could cool gas efficiently in the early universe. Webb's discovery of offset active galactic nuclei suggests that black hole mergers were common in the early universe. Several galaxies show spectroscopic evidence of dual AGN or spatially offset black holes, signatures of ongoing or recent mergers. The galaxy Sears 1746 shows 2 distinct nuclei separated by just 5,000 light-years, both showing broad emission lines characteristic of active black holes. These cosmic train wrecks were assembling the supermassive black holes we see in modern galaxies. The detection of molecular hydrogen in galaxies at redshift greater than 7 reveals that molecular gas, the fuel for star formation, formed efficiently in the early universe. H2 doesn't emit strongly in typical conditions, making it nearly impossible to detect directly at high redshift, but Webb's sensitivity reveals H2 absorption and weak emission in several early galaxies. This molecular gas formed despite the absence of dust grains that catalyze H2 formation in modern galaxies, suggesting alternative formation pathways. Analysis of gravitational arcs, the distorted images of background galaxies lensed by foreground clusters, reveals dark matter distributions that challenge cold dark matter models. Some early galaxy clusters show dark matter concentrations higher than simulations predict, while others show unexpectedly flat profiles. The cluster MAX J 0416-2403, observed lensing galaxies at redshift 10, has a dark matter profile that would require special formation conditions or modifications to dark matter physics. Webb has captured evidence of galactic fountains, cyclical flows of gas expelled by star formation and later falling back onto galaxies. The galaxy SPT 2147-50 shows both outflowing and inflowing gas, traced by different ionization states and velocities. This cosmic recycling was already established when the universe was 700 million years old, providing a mechanism for galaxies to regulate their growth while maintaining fuel for continued star formation. The discovery of grand design spiral galaxies at high redshift challenges galaxy formation theories. The galaxy Cosmos 2112 shows perfect spiral arms at redshift 3, when such organized structures shouldn't exist. Spiral arms require specific conditions: a rotating disk, appropriate gas density, and stellar populations of the right age. Finding grand design spirals so early suggests that galactic dynamics evolved faster than our models predict. Observations of the Lyman continuum escape fraction, how much ionizing radiation escapes galaxies, show dramatic evolution with redshift. Early galaxies were remarkably porous to ionizing photons, with escape fractions exceeding 50% in some cases. This high escape fraction helps explain how the universe reionized so efficiently, but raises questions about what made early galaxies so transparent to their own radiation. The detection of supermassive stars in early galaxies rewrites our understanding of stellar physics. Webb's spectroscopic signatures suggest some early galaxies hosted stars exceeding 1,000 solar masses, behemoths that shouldn't be stable according to standard stellar models. These hypothetical supermassive stars would burn through their fuel in just a few million years, exploding as hypernovae or collapsing directly into intermediate mass black holes. The galaxy CR7 shows helium emission patterns that might indicate such monsters existed when the universe was just 800 million years old. Webb's multi-wavelength observations reveal that cosmic dust evolved differently than expected. Instead of a gradual build-up from successive generations of dying stars, dust appears suddenly and abundantly in early galaxies. The galaxy A1689 at redshift 8 contains as much dust as galaxies billions of years older. This rapid dust production suggests that early supernovae were incredibly efficient dust factories, or that alternative dust sources, perhaps direct condensation from metal-enriched gas, operated in the early universe. The discovery of void galaxies at high redshift challenges our understanding of environmental effects. These isolated galaxies, living in cosmic voids far from any neighbors, still show rapid evolution and metal enrichment. The galaxy HDF 850 at redshift 12 exists in a void spanning 50 million light-years, yet displays a complex structure and ongoing star formation. This suggests that internal processes, not environmental interactions, drove early galaxy evolution, contradicting models that emphasize mergers and interactions. Temperature mapping of galaxy clusters through the Sunyaev-Zeldovich effect reveals that intracluster gas was already shock-heated to millions of degrees very early. The protocluster SPTCLJ 2106-5844 at redshift 4.3 shows gas temperatures exceeding 10 million Kelvin, indicating massive galaxies were already falling into the cluster and heating gas through gravitational compression. These early clusters were already processing baryons the same way modern clusters do. Webb has detected fluorescent emission from the first galaxies illuminating surrounding gas clouds. Like cosmic light bulbs turning on in a dark room, these galaxies caused nearby gas to glow through photoionization. The patterns of fluorescent emission around galaxy clusters at Redshift 7 mapped the three-dimensional distribution of gas and the escape of ionizing photons. We're literally seeing the universe's lights turning on and illuminating the cosmic darkness. The discovery of tidal dwarf galaxies in the early universe reveals that galaxy formation wasn't always a top-down process. These galaxies form from material torn off during galaxy collisions, creating new stellar systems from recycled material. Webb has identified several candidate tidal dwarfs at redshifts greater than 6, born from cosmic collisions when the universe was less than 1 billion years old. These second-generation galaxies complicate our understanding of galaxy demographics and chemical evolution. Spectroscopic observations reveal that some early quasars are surrounded by enormous reservoirs of molecular gas. The quasar J2310 plus 1855 at redshift 6.3 is embedded in a gas cloud containing 10 trillion solar masses of molecular hydrogen, enough to fuel star formation for billions of years. These cosmic reservoirs explain how early galaxies could grow so massive, but raise questions about how such enormous gas clouds assembled and remained stable. Webb's polarimetric observations reveal that early galaxies had organized magnetic fields. While Webb can't directly measure magnetic fields, polarized light from dust grains aligned with magnetic fields provides indirect evidence. Several galaxies at redshift greater than 5 show polarization patterns indicating coherent galaxy-scale magnetic fields. These fields would affect star formation, gas dynamics, and cosmic ray propagation, adding another layer of complexity to early galaxy evolution. The discovery of blue compact dwarf galaxies at high redshift provides clues about the universe's first galaxies. These small, intensely star-forming systems might be modern analogues of the first galaxies. Webb finds them in abundance at redshifts greater than 8, suggesting they were the universe's first stellar nurseries. Their compact size, intense radiation fields, and rapid evolution make them ideal candidates for driving cosmic reionization. Analysis of absorption line systems reveals that metals were already mixing efficiently in the intergalactic medium. Webb's high-resolution spectroscopy detects carbon, oxygen, and silicon absorption from gas clouds that never formed stars. This enriched intergalactic gas must have been polluted by galactic winds from even earlier galaxies. The mixing appears remarkably uniform, suggesting that feedback processes operated efficiently from the universe's earliest moments. Webb has captured galaxies in the act of quenching, shutting down star formation permanently. The galaxy Cosmos 1-136-2 shows signs of rapid quenching at redshift 5.5. Its spectrum reveals both young stars and signatures of abrupt star formation cessation. Something, perhaps AGN feedback or environmental effects, shut down this galaxy's stellar factory while the universe was still young. Understanding this quenching is crucial for explaining the bimodal distribution of modern galaxies into star-forming and quiescent populations. The discovery of extremely blue galaxies reveals stellar populations we've never seen before. These galaxies have colors bluer than any local galaxies, suggesting stellar populations with virtually no metals and possibly top-heavy initial mass functions. The galaxy Glass Z12 has ultraviolet colors that require either pure population 3 stars or exotic stellar populations outside our current models. These cosmic sapphires might be our best glimpse of the universe's first generation of stars. Observations of radio galaxies at high redshift reveal that supermassive black holes were already launching powerful jets early in cosmic history. The radio galaxy TGSS J1530 plus 1049 at redshift 5.7 shows jets extending over 1 million light-years. These jets require stable supermassive black holes with strong magnetic fields and accretion disks, a level of organization that shouldn't exist so early. The universe's most powerful engines were already operating at full capacity. As we stand at the precipice of cosmic understanding, Webb's revelations force us to confront a humbling truth. The universe's edge isn't just a boundary in space, but a frontier of knowledge where our theories crumble and our assumptions shatter. The galaxies Webb has discovered at the dawn of time aren't just distant objects, they're messengers telling us that cosmic history unfolded in ways we never imagined. Every photon that traveled 13 billion years to reach Webb's golden mirrors carries information that rewrites textbooks and challenges the foundations of cosmology. The cumulative impact of Webb's discoveries suggests we might need a new cosmological paradigm. The standard lambda CDM model, successful as it has been, appears incomplete. Perhaps dark matter has properties we haven't discovered, dark energy varied in the early universe, or new physics operates at cosmic scales. Some theorists propose that the universe underwent phase transitions we haven't accounted for, periods when the laws of physics themselves evolved. Webb hasn't just found early galaxies, it's revealed that our cosmic origin story needs fundamental revision. The philosophical implications extend beyond astronomy. If massive evolved galaxies existed just a few 100 million years after the Big Bang, the universe's habitable epoch might have begun earlier than we ever dreamed. Ancient civilizations could have risen and fallen before Earth's atoms were even forged in stellar furnaces. We might be latecomers to a cosmic party that's been raging for over 13 billion years. The silence of the cosmos, the Fermi paradox, becomes even more puzzling when we realize how much time and space existed for life to emerge. Webb's observations of the cosmic edge reveal something profound about the nature of time itself. The galaxies at Redshift 20 exist at the boundary of observable reality, where time as we understand it begins to break down. Beyond them lies not just greater distance, but the approach to the Big Bang singularity itself, where space and time cease to have meaning. We're not just looking across space, but peering toward the very beginning of existence, approaching the moment when the universe sprang from nothing or from something we cannot yet comprehend. The discovery that galaxy formation was essentially complete by Redshift 10 means that most of cosmic history has been a slow evolution rather than dramatic change. The universe front-loaded its creativity, forming structures rapidly in its youth before settling into a more sedate middle age. We live in the cosmic afternoon when the furious star formation of dawn has given way to a steadier pace. Understanding this cosmic timeline helps us predict the universe's future, a slow fade into darkness as stars die and galaxies drift apart. The chemical enrichment patterns Webb observes tell us that the periodic table was essentially complete within the universe's first billion years. Every element needed for chemistry, biology, and life had been forged and distributed by ancient stellar explosions. The cosmos became fertile ground for complexity almost immediately after the first stars ignited. This rapid enrichment suggests that life's chemical prerequisites emerged much earlier than previously thought, expanding the temporal window for life's emergence throughout the universe. Webb's deep fields reveal that even the emptiest patches of sky teem with ancient galaxies. Every direction we look, we see the same story, a universe that burst into existence with astonishing vigor, creating structures of unexpected maturity and complexity. There are no truly empty regions, no gaps in the cosmic tapestry. The universe is wall-to-wall galaxies extending to the very limits of observability. This completeness suggests that galaxy formation was not a rare accident but an inevitable consequence of cosmic evolution. The discovery of massive black holes in the universe's infancy changes our understanding of these cosmic monsters. They're not endpoints of stellar evolution, but seem to be fundamental components that may have formed alongside or even before the first galaxies. Some theorists now propose that supermassive black holes were the seeds around which galaxies grew, rather than structures that formed within existing galaxies. Webb has inverted our understanding of the cosmic chicken and egg problem. As we process Webb's data, patterns emerge that hint at deeper truths. The distribution of early galaxies isn't random but shows correlations extending across billions of light-years. These patterns might reflect quantum fluctuations from the universe's first instant, magnified to cosmic scales by inflation. We're seeing the quantum mechanical origins of the largest structures in existence, a direct link between the subatomic and the cosmic, between the smallest and largest scales reality permits. The technological triumph of Webb itself deserves recognition. This telescope, delayed for decades and over budget by billions, has justified every dollar and every delay. Its hexagonal mirrors, aligned to nanometer precision while orbiting 1.5 million kilometers from Earth, represent humanity at its best, creatures of flesh and blood reaching across cosmic time to understand their origins. Webb is more than a telescope, it's a time machine, a portal to the beginning of everything. Looking forward, Webb's discoveries set the stage for even more powerful observatories. The proposed Habitable Worlds Observatory, the giant Magellan Telescope, and the extremely large telescope will build on Webb's foundation, pushing even deeper into space and time. Future gravitational wave observatories might detect the formation of the first black holes. Cosmic neutrino detectors could capture particles from the universe's first second. We stand at the beginning, not the end, of cosmic discovery. But perhaps Webb's greatest revelation is also its most humbling. The more we learn, the more we realize we don't know. Every answered question spawns 10 new mysteries. The early galaxies that shouldn't exist, the black holes that form too quickly, the chemical enrichment that happened too fast. These aren't failures of science, but invitations to dig deeper. The universe continues to surprise us, and that capacity for surprise is what makes science a never-ending adventure. As you contemplate these discoveries, remember that you're not a passive observer, but an active participant in cosmic evolution. The atoms in your body were forged in stars that Webb might have photographed. The water you drink has been cycling through space for billions of years. You are the universe becoming conscious of itself, using tools like Webb to understand your own cosmic ancestry. These aren't just pictures of distant galaxies, they're family photos from the universe's youth. The edge of the universe that Webb reveals isn't a wall but a horizon. Beyond what we can currently see lies more universe, possibly infinite, certainly vast beyond comprehension. Webb has pushed that horizon back, showing us galaxies from when the universe was just 2% of its current age. But even these ancient giants are latecomers compared to the first moments of existence. The true edge, the Big Bang itself, remains tantalizingly out of reach, a singularity where our physics breaks down and our understanding fails. In the end, Webb's journey to the cosmic edge reveals as much about us as about the universe. We are a species that builds billion-dollar machines to capture ancient light, that dedicates lives to understanding distant galaxies, that finds beauty and meaning in the cold mathematics of cosmology. Webb's discoveries don't diminish us by revealing our cosmic insignificance. They elevate us by demonstrating that insignificant creatures can comprehend the significant universe. We may be small, temporary, and fragile, but we can know and understand the cosmos that created us. The universe's edge remains a frontier, not a boundary. What Webb has shown us is not the end, but the beginning, the first glimpse of cosmic dawn, the universe's baby pictures, the moment when darkness gave way to light. These images and data will inspire generations of scientists, philosophers, and dreamers. Children looking at Webb's images today might solve the mysteries those images reveal. The cosmic story continues, and we're all part of it, made of star stuff, powered by fusion, contemplating our origins while hurtling through space on a pale blue dot, using golden mirrors to peer back toward the beginning of time itself. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. What is the largest thing in the universe? In this video, we journey from Earth to the edge of the observable universe, exploring the Milky Way, galaxy clusters, superclusters, the cosmic web, and much more. See you there.